What is the meaning of the word wave? And it is possible to give answer in one word, and that is disturbance. Every word in English language does not mean an object. So there are many things that are not objects. There are many things that you cannot hold. There are many things that you cannot even picturize. Because they are not objects. We try to find out some way of representing which type of disturbance are we talking about. We are talking about mechanical disturbance. To begin with, eventually you would see that it does not even have to be mechanical disturbance. But to begin with, let us talk of mechanical disturbance. Mechanical can be visualized, mechanical disturbance can be visualized very easily. Imagine a train of people. Or let me say queue of people. Maybe this queue is to get some movie ticket or some match ticket, whatever. But tickets are few. And person somewhere here senses that tickets are few and he is not going to get it. So, and he doesn't have a great character. So he decides to push the next person. Let's say this is a person who is pushing, this is the next person. He pushes his shoulders. So this pushing sort of transmits, but that push is not that bad that the feet would dislocate. Feet are firmly placed on the ground for everybody, but push goes via shoulders, so some bending is there. Several people are disturbed due to that. Mechanical disturbance of this sort is possible in so many different ways. You cannot really hold, this is not an object, right? How can you hold it? You can only feel it. So in the strict sense, there cannot be a picture of wave. Right? In the strict sense, there cannot be any picture of wave because it is not an object. But we do find a way of representation. Mechanical disturbance can be of various types. Look at this case. It's a long string, tight long string. A man just jerks it up, down, that's it. Up, down. That creates slight deformation, and that deformation proceeds forward. Deformation proceeds forward, not this particle. This person did not reach here, did not walk feet, no movement of feet. But this person knows that there something is happening. This person did not reach there. The key idea is that this particle doesn't travel here. What happens is that disturbance travels. Disturbance travels. So earlier this particle was quite happy, not moving at all. But then suddenly somebody from neighborhood disturbed it, and at this very moment it has to go up. It is up now. This particle has gone up, thanks to its neighbor. But then it may not be a permanent state. For example, this particle was here at this very moment, and then it is back. So this is not a permanent displacement type of thing. Back. So we are never going to say that particles travel from point A to point B. No. These fellows don't travel to the right side. But what travels is the disturbance. This particle would say in this situation that I am disturbed. I was happy and now I am disturbed. This particle will say here that I am disturbed. But it won't say the same thing here, that I am disturbed. It won't say that here. It will say that here. So one needs to understand repeatedly that it is disturbance, disturbance, disturbance. Particle may be having speed here. Different particles may be having speed there. That is the speed of particles. Speed of disturbance has nothing to do with speed of particles. Disturbance can travel slowly. Disturbance is traveling to the right side. Particles are moving up or down in this example. So particle speed has nothing to do with disturbance's speed of. This is good for beginning because at least you can see something in these examples. Otherwise, what do you see if I talk about X-ray moving? You don't see anything. You don't hear anything of X-ray moving. In case of sound, you hear, but you don't see. In case of blue color or any other color, you can see, but you don't hear. In case of X-ray, neither do you see, nor do you hear. So you are dependent on some instruments that tell you that there is something called X-ray, otherwise you won't even know. Mechanical disturbance, if it is there, then these disturbances or these waves are called mechanical waves. And sound wave does require medium, particles. It requires particles. So if you go to such a planet where there is no air, then in open you cannot talk. Sound can travel through solid, yes, but it won't work that effectively. If you want to talk through your body, sound passing through your body, then through the ground and through the body of the other person, it won't be very effective. It does work on some occasions. Sound through the solid or even through the liquid for that matter. Sound is a mechanical wave. But if you talk about light, then between sun and earth or distant stars and earth, nothing is there. In a large part of the space, and still we get light, not just light, other radiations also we get. Heat is not light. I mean, it is electromagnetic radiation, but not visible light. So that is another type of wave in which you don't need medium. Then this type of picturization becomes hard. That one particle kicking another particle, that particle kicking another particle. There are no particles that are kicking when light is moving in vacuum. But then there are fields, electric field, magnetic field, etc. So instead of talking about particles displacement, we talk about amplitude of electric field or magnetic field. So those things change in those waves. Non-mechanical waves. Time to do some maths. When we talk about waves, some waves proceed forward. They are called progressive waves. Some waves are just standing waves. Like a guitar string. When one plays guitar, what happens in guitar strings is stationary, standing wave or stationary wave. Now, there are other vibrations. For example, there may be vibrations of air. String is vibrating, right? That is one thing. But air is also vibrating. You know how music instruments have got, some of them have got rather big dome type of thing. We want air to vibrate. Sitar has big one. Acoustic guitar also has not that big, but yes, reasonably big. So air vibrates. So while string vibration could be a stationary wave, a listener who is sitting 2 meters from guitar or 5 meters from guitar, that listener can hear because it is a progressive wave as far as air vibrations are concerned. Air particle kicking another air particle, that is a progressive wave. But as far as the string of guitar or sitar is concerned, that is a standing wave. So you have got progressive wave, you have got standing wave. We first will talk about progressive wave. This example is of progressive wave. That bump is proceeding towards the right side. There are two parameters that you need to look at. Time also and X also. This particle may say, at this very moment, that I'm happy. I'm not moving anywhere. But that is the story of this particle at this instant of time. After some time, the very same particle may not be able to say the same thing. After some time, that particle may be somewhere up. So even if we are talking about one particle, we cannot give a permanent answer that that particle will be displaced or not. How much will it be displaced? Some particles are displaced more, some are displaced less. We cannot give a permanent answer to a specific particle because time dependence is also there. Right now this particle is not displaced. Right now this particle is displaced. After some time the situation would be different. So be prepared for little complexity now because of the dependence on both of them, T and X. Yes, if I fix time, if I say, okay, freeze time, then only X dependence would have been there. For example, this is a freeze time is like taking photograph. take a photograph of the string. Time is frozen. So if picture looks like this, it's so easy to discuss. This particle is here, this particle is here, this particle is here, this particle is here. It becomes so easy because time is not moving. Once you have taken the picture, you have frozen the time. If I take a picture of this situation, again very easy. That is because I have made t constant. But in real situation, you give a jerk up and you watch. And you watch it traveling to the right side. Time is also changing. And x0 to x equal to total length covers so many particles. So that's why some complexity is bound to come. Alright, so how do we handle it? We say, we focus first at x equal to 0 point. Just watch it, x equal to 0 point. Let time change, only watch this point, nobody else, watch it. And suppose its behavior, this point's behavior is given by f of t function. It could be some complicated function or some simple function. But this function is telling only about this point, f of t. So maybe in the beginning it was here, then it came here, here, down. All those things f of t is telling us, but only for this particle. Alright. Now let us say the disturbance is traveling to the right with a constant speed v. Constant speed v. This is not a bad approximation. Generally sound travels with constant speed under given conditions. Light travels with constant speed under given conditions. So disturbance. Speed of the disturbance is v. It has nothing to do with speed of the particles. After time t, what will happen? This disturbance will reach somewhere else. Let's say I'm interested in this point x. After how much time will this disturbance, this doesn't have to be 0 by the way, f of t can be anything, it can be this height or this height, whatever it is. So after how much time will this disturbance reach here? If it was this much, exactly this much will be here. After how much time? If this is x and this is v, don't bother about this bump, it is very, very small. This is exaggeration in drawing. This is very, very small. You can ignore its curved behavior. Take it as x only. Not a difficult question. V is fixed.
X by V.
V is fixed.
X by V.
X by V.
Sir, x by
Yes.
v.
X by V. So after x by V time, this disturbance will reach here. Now please read all those statements very carefully and let me know if anything is not clear. So if you understand it, then it's good, because this is one of the difficult parts of this topic. So the equation of progressive wave is f of t minus x by v, where f of t is y, or the disturbance of the particle at x equal to 0. If f of t is the disturbance of the particle at x equal to 0, then for any general particle x, this would be the disturbance, and that disturbance itself is the equation. F of t could be of different form, f of t. Now that means you can have several possibilities. F of t is some function of t, so it could be complicated, it could be simple. All those cases are possible, but it doesn't trouble us. The good news is that on most occasions, f of t is not arbitrary. Theoretically, f of t can be arbitrary. And whatever f of t is, this is what would be your answer. So if this is what happens in most cases, then our job is quite or much more simple. This is nothing but SHM. So imagine that person is moving hand up, down, up, down, up, down periodically. Basically, his hand is performing SHM. A sin omega t. And therefore, you don't have a pulse, but you have got a train sort of a thing. And the string will actually look like this. It will actually look like this. But technically, calling this as wave, technically speaking, is not accurate because it is string. But often sinusoidal curve is called as wave. Wave is a disturbance, and this particle is disturbed in this manner. So for this particle, if it is this, then this is what it would be for a general particle. And we say when we say for a general particle, it is the equation of the progressive wave. So equation of progressive wave, sinusoidal I should say, equation of progressive wave is this, f of t minus x by v. No matter how that person moves his hand, whatever f of t he is able to generate, this is what the answer would be. If he is able to move his hand in such a way that he is able to generate this behavior for that particle on the left, then this is what the wave would be, wave equation would be. And we like to write it in this manner, omega t minus kx where k is omega by v. V is the wave speed. What is omega? Well, you know SHM motion. So whatever omega is for SHM motion, it's the same omega. Amplitude is amplitude of that SHM. K is omega by v. We are now going to define wavelength. Some particles appear to be in synchronization. Some particles appear to be in synchronization. Synchronization means y is same, displacement, velocity is also same. Displacement is same, velocity is same. Look at these two for example. And this also. I can have several such particles. They are in synchronization. The shortest distance between them is called the wavelength. it may give an impression, wrong impression, that you have got some long thing and you're trying to measure its length, and you are calling that as wavelength. That's a wrong picture, because wave is not an object. Wave is not that string which is shown on the board. This distance, shortest, is called wavelength. So two conditions. Y should be same for both. Velocity should be same for both. Our great emphasis would be on sine wave. Our major emphasis would be on sine wave, though you should have the capability to handle other f of t's also, which is not a problem. Alright, first let's find out something about wavelength for sine wave. So y is given by a sine omega t minus x by v. So for this particle and for this particle, y is same. So one trigonometric equation would be this, and then velocities are same, so their derivatives are also same. So differentiating, all right, they are both same. When does it happen that sine and cos both functions are equal? Yes, any answer?
Sir, at pi by 4.
Oh, what I mean to say is, when does it happen that this is also true and this is also true? I'm not asking sine alpha equal to cos alpha, but these two both are true. When does it happen? And the answer is when this condition is fulfilled. If I ask you only this, then you would say that sine 180 minus theta is sine theta. If I ask only this, then your answer would be something. But both of these have to be satisfied. The answer can only be this, 2 pi gap. Sine and cos are periodic functions. When do they repeat? That's what the question was about. Together they repeat after 2 pi, together. 2n pi rather. So if I want shortest, I would take 2 pi. And I want shortest for lambda. So right now I'm writing this, but because I want shortest, I would choose 2 pi. I hope this point is clear. If you have any questions about it, let me know. Now, what did we say about omega? We said that that person is able to move his hand up, down in such a way that his hand is performing vertical SHM, A sin omega t type, and omega and A are defined the usual way you define an SHM. So A is the amplitude, and if we say t is the time period for that SHM, then t would be omega by 2 pi. So this t is for SHM. Now, I think in this whole discussion, one difficult part was this. Now, one more difficult part will come. Capital T, we said, is related to omega, and that has to do with SHM, particles motion. There are two things here, particles motion and wave motion. What we are going to say is something big now. We are going to say that capital T is same, whether you talk of particle or wave. What it means is this. That is the thing which connects the two motions actually, capital T. Okay, I won't complicate it too much. This much should be enough to understand that. Look at this and that. They are in synchronization, right? When this goes down with some velocity, this goes down with the same velocity. Their y's are same, their v's are same. So distance between them is lambda. This is performing SHM, whose time period is t. This is performing SHM, whose time period is t. Speed of the disturbance is v. Now, for just a moment, forget about this particle performing SHM. Suppose it is not performing SHM, wave is traveling to the right side. Maybe the string was straight, right? But finally, string, this part was disturbed. That's what happens. Many parts may be straight. Disturbance reaches those parts and they start getting disturbed, right? So maybe disturbance did not reach this point, but it reached this point. Now, we know that eventually these two are moving in synchronization. What is happening? Exactly the same thing will happen here. That means if this thing was here and was going down, after going down, up, up, down, down, up, up, down, one cycle will be completed, and that will involve capital time T, and then again it will go down. When disturbance reaches here, it does the same thing. It is like saying that when the wave was here, disturbance reached here, say this was going down, when it started moving down and neighborhood particles started getting disturbed, it went down, up, up, down. By that time, this fellow started moving exactly the same way. When this went down, up, up, down, came back, at that very moment this fellow also started doing the same activity. What it means is that the time it took to go down, up, up, down, in exactly the same time, wave traveled this distance. I repeat, the time it took to perform complete cycle exactly in the same time wave reached here. If the timings are not same, then these two cannot be in synchronization. This is the thing which connects two things that are happening, the particle motion and the wave disturbance, and the wave progression, Time is same. For one cycle, whatever time it takes, in the same time, one wavelength is covered, lambda. It's the same t. Speed equal to distance upon time I can use, because speed is fixed. So what we got here, we call this time as time for SHM, and it is the same time in which wave travels one lambda distance. 1 upon time is called frequency, and we have this famous equation V equal to nu lambda. This works for all types of waves, even though we got it for string case, it works for all types, whether string or not string, whether mechanical or non-mechanical. This is a universal result for wave, sinusoidal wave. And regarding K was how much? Omega by V. K was omega by V. And we said frequency was 1 upon T. Omega is 2 pi frequency upon V. V upon nu is lambda. This is generally very useful. K equal to 2 pi by lambda is very useful. K equal to 2 pi by lambda. So equation for progressive wave is this. It will depend on time also, it will depend on the location of the particle also. Remember, it came from this. We said the person is moving his hand. His hand is at x equal to 0 only, right? He's holding that string. So this gave us this. If you change this, this will change. For example, if I am holding a string, maybe I can move the string up in the beginning, but if I want, I can first move it down. So I can move it up, down, or down, up, down, up. If I, now you know sine function, sine in the first quadrant is positive. Up, down, up means positive. If I do it down, negative. A sine kx minus omega t. If I move my hand up first, I am doing something like this. If I'm moving my hand up first. But if I'm moving my hand down first, I'm doing something like this. So what will happen to this? This is the equation. You can take this minus inside. That's what you would get. Kx minus omega t. So some books take it as this. Some books take it as this. Both are fine. The only difference in these two is that how you started moving your hand up, down, or down, up, down, up. In both cases, wave is moving to the right side only. Yes, if you want to change the direction of velocity of the wave, that's a different thing. Both of these equations tell wave going in one direction only. Right? If you want to change the direction, in place of x, put minus x. That's it. In place of x, put minus x, whether here or here. And then you have a wave going in the opposite direction. Now you know that SHM doesn't have to be like this only. When we say sine omega t, we are basically saying that at t equal to 0, y is 0. So the person had his hand at the middle. And then he can do two things, take it up, take it down. Hand in the middle. Why is it necessary to have it in the middle? Maybe his hand was a little up. Maybe his hand was a little down. So generally speaking, SHM is given by this. Delta will tell the initial status. Was hand above that line of string? Was hand below the line of the string? So likewise, if SHM is changing, then final equation will change. Omega t minus kx, maybe plus delta type of thing. Omega t minus kx plus delta. Any questions in today's discussion? If you have, let me know. You will have to revise this topic every day as we do it. Alright, we stop now.